Hi, I'm Paul Gilman, and I work for the Midwest Renewable Energy Association. I teach the PV 431 course, which is about using NREL's System Advisor Model, or SAM, to model PV plus storage systems. I have a degree in electrical engineering, and I've worked for the National Renewable Energy Lab, or NREL, for over 20 years. NREL has several energy modeling platforms, and I've worked on a couple of them. Mostly on SAM, the System Advisor Model. So before online training was a thing, I traveled the world working with energy policymakers, educators, and project developers, teaching them how to use models like SAM to answer questions about their projects. I now work on the SAM software development team at NREL, so I know the model inside and out. Over the last few years, there's been a lot of interest in battery storage for residential and commercial buildings. Batteries can be used to shift electricity usage from times with higher rates to ones with lower rates, or to reduce demand charges for a business. They can also be used to store solar energy during the day to use at night. If you install battery storage systems, customers will want to know how much it costs to install and operate the batteries, how often the batteries will need to be replaced, and for a PV plus storage system, they'll want to know if including a battery with PV is worthwhile. Those questions are tricky to answer because they depend on so many variables, like the size and type of the battery, the electricity rate structure, the customer's electricity usage, and battery replacements depend on the type of the battery, how heavily the battery is used, the future costs of batteries. Because SAM combines a performance and a financial model, it can consider all of these factors and calculate metrics like the battery round-trip efficiency, net present value, and payback period that you can use to quickly compare and evaluate different design options. So PV 431 builds on PV 430, so it assumes that you know how to use SAM. And like PV 430, it consists of a series of videos explaining and demonstrating the steps for using SAM, and it's presented in 2 sessions. The first session goes over some basic battery storage concepts to define key terms used in the course, like energy arbitrage and peak shaving. It then walks through the steps for modeling a residential PV plus storage system that stores solar energy during the day and discharges it at night. And then the second session walks through a PV plus storage model for a commercial business that's designed to reduce monthly demand charges. And it also goes over options for modeling battery replacements. This course also comes with a handbook that has all of the information from the videos that you can use as a reference during the course and after you complete it. And like PV 430, when you complete the first session, you'll have to do a homework assignment and then proceed to the second session. And there's a final assignment to get credit for the course. These assignments give you a chance to communicate with me and get feedback on your work. PV 431 covers modeling residential and commercial PV plus storage systems in SAM. It covers topics like battery sizing, battery dispatch, replacements, and then how to interpret SAM results and use them in your work designing PV plus storage systems. It also covers financial aspects like the cost of installing, maintaining, and replacing batteries, and how to use metrics like the net present value to evaluate a project's feasibility. After the course, you'll have used SAM to model a residential and a commercial PV plus storage system. You'll be familiar with the software's user interface, how to enter data into the model, and how to interpret the results. When you're done with the course, you'll be ready to use SAM in your work, whether it's helping customers understand how a system you're proposing will work, designing your own system, or just learning about solar energy and storage. I hope you'll consider taking PV 431. I look forward to meeting you during the course. Thank you.